If you haven't done so yet, please pause the video and attempt the question on your own before moving on. We can begin to solve this question by drawing a picture. So we have called the negative charge Q2 and the positive charge that's fixed Q1. Initially, they are a distance of 1.6 micrometers away from each other, and then the negative charge moves until it is 0.5 micrometers away from the positive charge. And at that point, it is moving with a certain velocity, so we can include some little swoosh marks to show that it is now moving. Initially, of course, it is at rest. And it turns out that we can solve this question by using the conservation of energy. And in the conservation of energy, we have the initial energies equaling the final energies. We have denoted the electrical potential energy as EPE, and then the kinetic energy as KE, of course. And since the particle is released from rest, we know that the initial kinetic energy is 0, so we can actually cancel that out. And since part A of the question is asking us to find the kinetic energy, we can subtract the EPE final from both sides of the equation, and that way we can isolate the final kinetic energy. Now, actually, this equation is written sort of backwards. Why don't we just flip it around so we can put the KE final on the other side and these electrical potential energy terms on the right side. Now, to proceed, we need to remind ourselves what the formula is for electrical potential energy. So, electrical potential energy is equal to the Coulomb constant times the two charges divided by the distance between the charges. So for the initial electrical potential energy as well as the final electrical potential energy, we're going to substitute in this expression here. Note that for the distance, we will use Ri to denote the initial distance, and then Rf to denote the final distance. So we've made the substitutions, and then we're going to notice that both terms on the right side of the equation contain the same term K, Q1, Q2. So we see it there, and we also see it here. It's pretty convenient to factor that out of the equation. So let's take a look at what that would look like. So here we have that term, that K, Q1, Q2, factored out of the equation. Notice that the distances are on the denominators of the fractions, and that's because originally they were located in the denominators of the fractions. So we have to make sure we make it 1 over the R value as opposed to just the R value. Now with the K, Q1, Q2 term factored out of the equation, we can now begin to plug in the known values. Notice, though, that we have to change things into standard units. So, for example, the initial distance between the charges, this Ri, was given to us as 1.6 micrometers. We have to make sure we convert that into meters by multiplying it by 10 to the minus 6. Same thing with the final distance between the charges. We'll have to call that 0.5 times 10 to the minus 6. Also, the charges themselves were given in nanocoulombs, so to convert that to the standard unit of coulombs requires us to multiply by 10 to the minus 9. So we'll have to do that for both charges. And then finally, the value of Ke is a known value. It's 8.99 times 10 to the 9th. That's going to be the value we plug in for Ke. So with all those ideas in mind, let's plug in the known values. Voila, here it is. We have all the values given in the question plugged into the formula. And when you carefully plug this all into your calculator, you should get approximately, we'll have to come up here, we're running out of room, approximately 0.294 joules for the final kinetic energy of the negative charge, the charge that we had called Q2. And that is indeed the correct answer to part A of the question. Now, to solve part B, we just have to recall the following equation for kinetic energy. And since the question is asking us for the speed, we just need to solve this for the speed, which is v. So we'll have to multiply both sides of the equation by 2. We'll do that on the right side as well as the left side. We can then divide both sides of the equation by m. And then finally take the square root of both sides of the equation. Now, to calculate the speed when it's 0.5 micrometers from the fixed charge, we just have to plug in the kinetic energy when it's 0.5 micrometers from the fixed charge, and we already have that value. So we're going to plug that in for the kinetic energy, and then the mass of the particle was given to us in milligrams, so we'll have to convert that to kilograms by multiplying that 8 by 10 to the minus 6. So there we have all the values plugged in, and when we compute that, we get approximately 271 meters per second for the speed of the charge, and that is the final answer. Thanks for taking the time to watch the video. If you liked it, please subscribe to the channel so you could stay tuned for additional videos. Also, you are welcome to send in your own question to the email address shown, and I will do my best to post a video solution to it on YouTube.